Hi, I want to talk about a functional group that you might not have seen yet called an imine. Now, the imine, what we're going to do in this lecture is we're going to kind of follow on actually trying to think about what this might look like, not just give you the answer, but think about what happens in this reaction over here when we have these components and try and work out what that product might be. And we'll take it through kind of like a mechanistic thinking to get to the product. Now, imines are formed when we react with an aldehyde or ketone and a primary amine. And let's just see how this reaction occurs. So what we do know is that nitrogen has a good lone pair on it, which makes it a very nice nucleophile. Amines are good bases and so good nucleophiles. And we know that a carbonyl is certainly an aldehyde is a really good electrophile. And so any kind of, nucleophile is going to want to add to that over there. You'll notice here that I have added some acid over here. And that's actually something which should give us some pause to stop here and think a little bit about what is going on here. Because if we've got an acid, H+, and we have an amine, which is very basic, and we've also got lone pairs on the carbonyl there, the reality is that the amine is going to pick up the acid. But the minute the amine picks up the acid, it has no more lone pairs. And so it can't do the reaction that we're thinking would happen. So if we had one equivalent of this and one equivalent of this, no reaction is really going to occur. However, if we are just having a catalytic amount of the acid, maybe 10% or less, 5%, a little bit of the acid, then that means that, yes, while this acid will protonate some of the amine, there's definitely going to be amine free, which can then do the reaction. And if we do the reaction, we should be able to work out that the nucleophile will go to the electrophilic carbon and we'll break those bonds over there. And this would be an equilibrium reaction, which would give us an O- over there and an N and an R. The nitrogen would be positively charged. All right, now, doing a reaction like this, there is a small problem that I have. And the problem I have is that we've generated an O- over there. And an O- is an extremely strong base. So we've gone from something which is very neutral over here. This is neutral, this is neutral. And we've generated an extremely strong base over there. And for me, that is problematic because, that would not just exist. So in terms of this equilibrium over here, the equilibrium would absolutely lie on the side over here. Yet this can go forward. And when it goes forward, it can go forward because there is acid in this reaction. And so this negative can go and pick up an H+ like that. And one of these protons can leave. And we're going to get effectively a proton transfer reaction, which we often write as PT, standing for proton transfer. And we get this as an intermediate product. Now, technically, this H over here came from the acid, but of course we've regenerated a new one, a blue H, so the blue and the pink become the same effectively. All right, now when I do this mechanism, I sometimes, what I tend to do, and it's totally fine if you do it this way, I like to do it because I think it just keeps mechanistically the same thing happening every time that we work with a carbonyl. I actually usually protonate the carbonyl first. So I'll take the lone pair and protonate it with the acid. Where's the acid coming from? Well, it's also coming from the solution. The acid will want to absolutely associate over there. Some may associate on the lone pair of electrons on the oxygen. So it is okay to draw it that way. But if you draw it this way, where you first generate the negative and then protonate it, that's also totally fine. At this point over here, we actually form an intermediate called a hemiaminal. We're not actually going to cover aminals in this course, but aminals are situations where it's like a nitrogen equivalent of an acetal. So we've got two nitrogens. So this is like the nitrogen equivalent of a hemiacetal. So we have an OH and then an O and something like that. So that's what it's called, is a hemiaminal. But at this point over here, something else wants to happen. And we don't go to the full aminal like we did with acetals. And the reason we don't do it is because if we follow the mechanism, we see something, what happens next, and we can see why. So we do exactly what we've done before in previous examples. This OH over here can be protonated by another acid, so it's got lone pairs, and we change it into a good leaving group. And so we end up with an OH2, positively charged, and the amine. And now, exactly like in the acetal formation, you've got a nitrogen, in acetal formation, you formed the oxocarbenium, the oxygen donated its electrons in. Now the nitrogen, which actually can donate its electrons in even better because it's the lone pair is stronger, higher HOMO, it donates those in and kicks out the water. And the product that we get for that, this over here, which is at this point called an iminium, because it's an imine, but it's protonated. But when this leaves, so the proton leaves as an H plus like that, regenerating the catalyst that was formed in the beginning, we get our imine, which is the final product over there. And I'll just draw it at the top. So we've got iminium and imine. So a couple of new words to learn over here. And we end up over there. Now, the reason that this over here is stable, the oxocarbenium and the acetal wasn't, because the oxygen couldn't have 3 bonds to it. So it was positively charged when this was oxygen. At this stage over here, the nitrogen itself is now fully neutral. And to add anything else over here, you're going to form a tetrahedral intermediate, which is a little bit more sterically bulky. It's one of the reasons why we always want to collapse down to the aldehyde or ketone, and we've seen this in the other examples. So the imine is actually pretty stable. This whole reaction is an equilibrium, and we can take imines under acidic conditions, adding water, and we can throw it back to the starting materials, or we can push it forward if we can somehow drive the water off. And for that, we can go to one of the ways is with Adine Stark. That's one of the ways. And another way, which I've used a lot in the lab, is using molecular sieves. All right. Now, molecular sieves are a special sort of solid material, which they have pores in them, and inside the little pores are big enough for water to get into. So what they do is they act like kind of sponges. So in your reaction, they sort of suck up the water and they can push an equilibrium off to the right. You can reuse the sieves. You stick them into a high oven to drive off the water, and you can reuse them again. So that's great. So these are two options for driving water off into a reaction. Now, imines are important intermediates. We're going to see them used in another lecture for why we use them. But in biological systems, an imine actually tends to have a different name. The name that they use there is a Schiff base. So those of you who are studying biochemistry, you will almost certainly hear this term being come up a lot. A Schiff base is just an imine. So you'll have a protein, which is a primary amine on it over there, and you'll have some ketone or aldehyde, and these two things can combine and you form the imine, and they're important intermediates. One thing I just want to discuss a little bit about here in terms of the imine formation is just coming back to this acid catalyst that's present over here. The first step of the reaction to get to this hemiaminal actually doesn't need any catalyst at all. So the proton that was picked up over here by the O- could have effectively come from one of these, from the ammonium proton over there, because that's very acidic. So we don't actually need it. These reactions do occur quite fast without acid. So that's why it's okay to draw this mechanism with a minus, even though I suggest maybe not. But the next step, to go from the hemiaminal, which is also really unstable, to the slightly more stable imine over there, you do need to have an acid. And then the problem is that we can't have a full equivalent. That's why we said that we need to have it catalytic. And so typically to do these reactions, you need to do a reaction at kind of a pH which is just slightly acidic. And so what we're aiming for typically in these reactions is the pH needs to be around about 4 to 6. That's kind of the sweet spot for these types of reactions, if you can do it in that range. And So it really ultimately means that you just need a catalytic amount of acid. And you can add tosic acid as an example, which you've seen in a previous lecture, just a catalytic amount of that. I want to look now, imines occur whenever we have a ketone or an aldehyde and a primary amine. But something different happens when we have a secondary amine, because a secondary amine has two R groups on it. And let's have a look at what happens there. So with enamines, this is a slightly different functional group that occurs when we use a secondary amine. And so what I'm going to do is I'm going to take a little bit of a shortcut. The mechanism here is exactly the same to a point. And that is how we would combine those two. So of course, we've got the lone pair of electrons and the nitrogen. It wants to add to the carbonyl. That's going to go up over there. We're going to protonate it, and we're going to go through the second step as we would to form the imine. So there's a couple of steps, mechanistic steps, that it would take to get to this point. But what we're going to do is we're going to end up with something that looks like this. And this is where sort of the problem comes up. So we'll end up with an positively charged nitrogen like this at this point, which doesn't have a hydrogen which it can leave to form an imine. In fact, it has to stop at the iminium. So the iminium is something that it stops, and these are actually quite important intermediates in reactions which we learn much later on in chemistry. But what is important at this stage is to realize that there is something else that can happen at this point of here. Now, secondary amines are a lot more bulky, so it is a problem for another amine to come in here to form some kind of aminal. That's the nitrogen equivalent of an acetal, as we said earlier. But what happens here is that, and this is going to feel kind of weird, but let's just look at the chemistry behind it. This proton over here, even though it is sitting on a carbon, and you would think it would have a very high pKa, because of this positively charged nitrogen, this proton turns out to be quite acidic, because when you put a negative charge here on this carbon, it can delocalize into form a pi bond and neutralize this nitrogen over there. So a base that can be used over here to pick that up needs to be a fairly weak base. And it turns out that we've got bases present. In fact, we've got base in the form of amines over here. So the amine base, and we can use that as the example, if I draw that correctly, can pick up the proton, either one, and these electrons can kick in to form a pi bond, not a C minus, but a pi bond, because this can break over there. And again, this is an equilibrium. We can form the product, which is our enamine. In this course, we need to just be able to recognize that this is what happens. As we go from an iminium, a secondary amine generates an enamine, we need to be able to recognize that. Later on in further courses, we're going to delve into this a little bit more. So that's why we need to lay this foundation now. We're going to see certain things. For instance, this methyl group I've pointed up over here, does it go down or does it go up? Depends a lot on the R group. So there's a lot of the stereochemistry of that double bond which needs to be looked at. But we're not going to deal with that right now. But it is important to realize that if we're going to form an imine, we must have a primary amine, because a secondary amine will actually get to an iminium, which almost always collapses then to the enamine, which is the stable neutral intermediate over there. And these can be used in reactions, so that's why they're quite exciting. Obviously, you should also think about that a tertiary amine would not be able to do any of this, because a tertiary amine, the minute it reacts, it's going to form a positively charged nitrogen, and it can't eliminate any protons, so it can't go any further. And that's why tertiary amines are good organic weak bases, triethylamine as an example. Okay.